we started to take a look at the deep convolutional networks. Okay, the fundamental idea in these networks was that we will have basically two steps to it. Okay, we'll basically try to extract features. Okay, then once the features have been extracted, then we will do the classification. So some input is fed. Okay, so this is where a lot of convolutions will occur. So after applying convolutions, by the way, the input doesn't have to be an image. It could be, for example, speech data. It could be text type of data. So convolution can be applied to any signal, right? The key thing to remember was that as far as convolution is concerned, in the continuous domain, once again, if this is h of t, we feed in some x of t. The output is related to the convolution of the input, and this is referred to as the impulse response, meaning if we give it a delta of t as the input, right, and delta of t once again has infinite amplitude, zero width over here, such that the integral of delta t from negative infinity to infinity is 1, right? So anyway, the actual integral, as you guys saw, was from minus infinity to infinity, x of tau, h of t minus tau, which, as we discussed, basically means invert it, slide it, and keep multiplying and integrating it. So essentially what it does is it tells us where the maximum overlap is occurring between two signals, right? So convolution could be in time domain, it could be in single dimensions, 2 dimensions, 3 dimensions, as many dimensions as we feel like it, right? Because our images are, eraser over here. Okay, because our images are typically 2-dimensional data. Okay, so essentially it's a bunch of pixels, 85, 92, and so on, right? So pixel values vary from 0 to 255, right? So the convolutions that we will do in a CNN will be both things. 2-dimensional discrete convolution, okay? If we have convolution in discrete domain, okay, so very similar to over here. So let's say we have h of n, y of n, x of n, then h of n will be given as k equal to, for example, negative infinity to infinity, h of n minus k, y of k. Okay? So integral changes to a summation, right? In 2 dimensions, because this is where we will be dealing with. Okay, so in 2 dimensions, for example, we can have h of, let's say, ij, y of ij. So if the output is y in 2 dimensions, right? So this could be k1 equal to negative infinity to infinity, k2 equal to negative infinity to infinity, let's say h of I minus K1, J minus K2, and K, what did I need? This should be X of K minus take over here. Okay, so X is the input, H, so we're doing a convolution between X and H, right? So this will be X of K1 and K2. Okay, so anyway, similarly, we can have convolutions in 3 dimensions, 4 dimensions, and so on, right? Okay, so we discussed this briefly in our last lecture. How does convolution take place on images? Okay, so if we have some image over here, bunch of values, pixel values, 60, 40, 30, 20, 20, 10, 90, 60, 80, and so on, right? Or let me put one more value over here, 30, 50, 40, 70, and so on, right? Okay, so once we do a convolution, so essentially what we are doing is, now we'll be doing a 2-dimensional convolution over here. Instead of H, this could be our, let's say, image I as an example, right? Or would be better to think of it this way, the X over here could be our input image, okay? K1, K2 basically, this, you can think of like, or ij over here is the X or the Y direction over here. So we'll be doing convolution with, instead of writing it as H, okay, we typically call it a kernel. Okay, which is the same thing as we did H over here. Okay, kernel could be a 3 by 3, 5 by 5, 7 by 7. Typically, the kernel is odd. So, for example, e.g., kernel could be, let's say 1, minus 1, 2, 0, 1, 4, 1. 2, 1, something like this, right? Okay, typically once we do the convolution, the sum of all the values should be 1. So 1 minus 1, 0, 2, 6, 7, 8, 10, 11. So in this case, a proper kernel would be divide the value by 11. Okay, so remember in convolution, like we flip one signal, we slide it and integrate it, right? Very similarly in discrete domain also. We will flip the kernel. We can do 2 things. We can flip the input and slide it over the kernel, or flip the kernel and slide it. In 2 dimensions, we rotate it by, so flipping in 2D is rotating kernel by 180 degrees. Okay, so we talked about it, right? So it was pretty straightforward. Row, so 1 minus 1, 2, and then 2, 4, 1, then 1, 2, 1, then 1, 0, 1. The center value stays the same. So this is after rotation by 90 degrees. And if we do one more rotation, so then if we further go over here and we do 1, 0, 1, so this row goes over here, 1, minus 1, 2, 4, 1, right? Let's see, 1, 0, 1, 1, 0, 1, minus 1, 2, 2, 4, 1, and 1, 2, 1, right? Okay, and then this goes over here. So now basically what we'll do is we'll superimpose this on top of it over here. So this will be 1, 2, 1, 4, 1, 0, and 2, minus 1, 1. So if you take a look at this evaluation over here, so essentially now we've already flipped the kernel, And so now we need to simply multiply and add. So the answer that we will produce in this spot over here will be 85 times 1 plus 60 times 2 plus 40 times 1 plus 20 times 4 plus 10 times 1 plus 90 times 0 plus 30 times 2 plus 50 times 1 plus 40 times 1, and whole thing divided by 11. Okay, so that would be the answer produced right in this spot, whatever that number is. And then we move the kernel to the next spot, do the same thing, multiply all of these by 1, 2, 1, and so on, right? Okay, so anyway, in short, it will end up producing the answer. Okay, so one reason I'm refreshing this is because today we'll be developing the backpropagation. So it's important to understand how the convolution equation looks like so that as we take the derivatives and so on, it becomes clear what we are doing. Okay, so anyway, this is the most important part for us. So if you can remember this, convolution in 2 dimensions, or let me summarize it even further. So the important concept to note down over here is, let's pick an example. So suppose kernel is 5 by 5. Okay. So then the convolution between the input image and the kernel, so I convolution K, mathematically would be expressed as 2 summations. Suppose I call the output to be y of ij. So that's the result of the convolution. Or let me call it c of ij. C of ij equal to input image convolution with some kernel. So this will come out to be p equal to minus 2 to 2, p equal to minus 2 to 2, I of I minus p. Ki minus p. Or let me make it even a little easier to follow. Let me pick different symbols over here. Okay, so suppose I call it u, I call it v. So this will become I minus u, j minus v times kernel of uv. So this is important for us to recognize. Okay, if we have a 5 by 5 kernel, then the convolution in terms of summation is expressed like this. Okay, and once again, nothing special over here. This is just a mathematical way of saying the same thing. Again, this means flip the image or the kernel. Like I said, we can do either one of them by 180 and then multiply with the kernel, keep sliding it. So either way, whether I write it like this or whether I write it like, so this is same as also writing it like I of uv and k of I minus u j minus v. Okay, but anyway, so let's just leave it like this for less confusion for the time being. Okay, so this is our convolution equation. Okay, now let's go create a CNN architecture. First, we'll try to understand exactly how the CNN is put together. Okay, then we'll take a look at how the forward pass goes through it, and then finally do the complete derivation of the back propagation through it, so that if needed, we can train it and see how that works, right? So now let me start drawing. oops, I have an eraser, so faster. Okay, so let me erase this so that I have more room over here to draw the picture. Okay, so the CNN architecture looks like this. Okay. We start with some image, and to make it easier for us to relate to, we'll pick the same example of our MNIST digits, so which we already know is 28 by 28. Okay, now unlike our dense networks where we had to convert it into a vector, then feed it to our hidden layer and then the output layer. For the CNN, we leave this as a matrix, meaning 28 by 28. We do not linearize it once we feed it through our CNN. So our architecture will first do many convolutions on this particular image, and each kernel will be different. Okay, so suppose we do K1 convolution, okay, and let's pretend this is a 5 by 5 convolution. Okay, so then what will it produce? What kind of output will it produce? As we discussed in the last lecture, this size minus this plus 1, right? So this will be 24 by 24. Everybody agrees? Okay, so then what we do is we add a bias to it. Okay, so let me call this B1 over here. Okay, and let me use the superscript over here to indicate this is for layer 1. Okay, so after we apply this, so we add some bias to every value. Then we pass it through an activation function. So each one of these 24 by 24 values will be added the same bias. So this is, for example, if the bias is 0.3, it will be added to each one of these 24 by 24 values. Okay? Then we pass it through an activation function, which could be sigmoid, ReLU, whatever we feel like it, right? Okay, so then as you can see, the output over here, what will be the size of this? Still 24 by 24. Okay, so then what we do is we pass it through what we call as pooling there. So let me make a pool over here, a pooling function over here, which basically will take the 4 values, take the average of the 4 values or take the maximum. So this pooling could be average pooling, maximum, max pooling. If it's the max pooling, whatever is the 4 numbers, the maximum of those will be replaced in that spot, right? And very similarly, we move to the next 4. So unlike once we do the convolution, we move the window 1 pixel to the right. Here, we'll be moving it 2 pixels to the right and so on. Okay, so the net result is the whole data will get reduced by half. So this will be 12 by 12. Okay. So that we can develop the back propagation nicely, right? Let's call this particular part over here C1 of 1. Okay, let me call this part over here, after 1 over here, CP, meaning C after the pooling, 1 of 1. Okay, so this is just the effect of one convolution and then the subsampling, right? Okay, very similarly, like I said, we do many of these. So let me go also put a K2 over here, which also will be 5 by 5. As you can see, this will be 24 by 24. Then we feed it to B2 of 1. and let me call this K2 of 1 over here. Then we feed it through an activation function, just like before. We get another 24 by 24. Let's call this C2 of 1. So this is the output of the second convolution after we have passed it through an activation function, right? Then we'll do a pooling. And then let's call this CP2 of 1, the first layer. Okay? Now, let's suppose we decide to do 4 convolutions in parallel, right? So the last one that we will do over here will be K4 of 1. Okay, then again, this will be B4 of 1. We pass it through the activation function, 24 by 24, then C4 of 1. And by the way, it doesn't have to be 4, could be 6, could be 8, could be 100, whatever we feel like it. Okay, then we pass it through a pooling function, and we get, in this example, CP4 of 1. Okay, so in the technical terminology, some people call these as the feature maps. Some people call this part the feature map. So these are called the feature maps. Okay, and this is the output of the subsampling layer. So this pooling is also called subsampling. So once again, if you, depending on what resource you're looking at, someone may call it, instead of pool, subsampling. Okay. So anyway, so popular choices over here, as I mentioned, are average pooling, max pooling, and min pooling. Okay. Either the take of the average of the 4 numbers. So all of them, as you can see, will produce 12 by 12 answer. Okay, so anyway, this whole thing is our first CNN layer. Okay, so now we can create more layers, but here's a small thing that you have to watch out, is the architecture of the first layer is different from the architectures of the following layers, okay? But the second layer, third layer, fourth layer will be identical, but the first layer will be a little bit different. Then once you see the whole picture, I'll clarify it further, and then you will be able to see. In reality, the first layer is not different from the second layer. It is actually a special case of the remaining layers as well. Okay, so now let's go to the next layer. So in the next layer, what we do is, for each one of these 4 feature maps, or the subsampling outputs, we further do convolutions. Okay, easy way to understand this is, we decide how many feature maps will we like to have in each layer. Okay, in this example, how many feature maps did we decide the first layer will have? 4. Okay, suppose we decide the goal is to have 6 feature maps in the next layer. Okay, so if the goal is 6 feature maps in next layer, okay, then what we will do is, we will apply 6 convolutions. Okay, so if, it doesn't have to be 6, like I said, we can pick it 8, whatever we feel like it. If the goal is 6 feature maps in next layer, then we will apply 6 convolutions to each feature map in first layer. Okay, so now let's go and start applying 6 convolutions. So if I go over here, okay, so each one will have a different kernel. So let's call this K 1 of 2. So meaning from the first feature map, we're going to the first output over here, but this is the second layer, so I'll put it 2, right? Same way, what will we call this? K?
2.
No, 1 going to, the first one going to
2.
2, and the layer is 2, right?
K
And-
1 3.
Okay, no, there are 6 of these.
4.
So this will be K
1 6.
1 6 of 2. Right? Okay, same thing over here. We will go okay, so this will be, as you can see, K 2 1 of 2, right? And this will be K 2 6 of 2. Everybody agrees?
Yes.
Okay, if we do a 5 by 5 convolution on a 12 by 12, what will be the
12
answer?
minus 5 plus 1. That will be the matrix.
8 by 8, right? So all of these will be
8.
8 by 8. Okay, and lastly, let me also do this over here. Okay, so this will be called K, what will we call this?
4. K 4.
4 1 of 2, right? 4 2 of 2, and this will be K
4 6 of
4 6 of 2, right? So how many total convolutions will occur over here?
6 4.
So 4 times 6 equal to 24 convolutions. Okay, so now, like I said, the second layer at first appears different from the first layer because if we want 6 feature maps, there has to be only 6 of these appearing at the end, not 24 of these. Okay, so then what we do is we basically add them. So this gets added to the first one over here. And so all the top one out of the 6 convolutions we are doing will get added. So how many additions are we doing over here?
4.
6. Not 4. 4 additions.
4.
So 4 additions over here. Okay, so then we will also add a bias. Suppose I call it B1 of 2. Okay. So then what will this produce? This will produce
A number.
what size will it produce? 8 by 8, right? And then we do pooling on it. And then after the pooling, what will be the size?
4 by 4.
Everybody agrees? Okay, so very similarly, let's go to another one over here. Okay, now what we'll do is add the second one. So the second from each one, the second from this one, the second from the last one, will get added. Pool and we'll get 4 by 4. And now, very similarly, let's go to the last one. Okay, so if I do the last addition, okay, so this is being repeated. So now the sixth one over here, okay, the sixth one over here, and the sixth one over here. So once again, each one of those is adding how many things? 4
Four of them.
additions, right? So again, we'll get 8 by 8 as the answer. Then we do the pooling, and then we do 4 by 4. Okay, so now how many of these are there?
6 of them.
So there will be 6 of these. And 6 of these, right? Oh, I forgot the activation function. The activation function will go. So let me put the activation function over here. Activation function over here. Activation function over here. So after the plus, you can see there's an activation function, right? Then we do the pooling. Okay, so this is our second CNN layer. Okay, so now what we do is, let's pretend, and by the way, suppose, I think Michael, you were curious how the next layer will look like. Let's say in the next layer we wanted 8 convolutions, okay? So how many further convolutions will we do over here? 8 of them, correct? 8 of them over here. Okay, so again, this will be K8, 1 of what? Sorry, K1.
K18 of.
Oh, yeah, K81. Because this is K1 of 1, correct? But now this is for layer 3. This will be for layer 3, correct? Similarly, this will be K8. Sorry, I reversed it.
Yeah.
It should be 1/8. And this will be 2/8 of 3, correct? Same way if we did okay, this will be K6 of 1 and K6 of 8 of 3. You guys agree?
Yeah.
So how many